Today we're going to be going over rules as to how to rank molecules by their acidity. And this requires for us to have some general knowledge of how acids and bases work. So acids are hydrogen donors, meaning they donate protons, also called hydrogens, to bases, which are hydrogen acceptors. So if we look at how this works, we have a base which has a lone pair right here. This lone pair is used to form a bond with hydrogen, forcing our hydrogen on our acid to break its bond with our acid. This leaves us with our base with its hydrogen attached, and our oxygen from our acid now has this lone pair, giving it a negative charge. So our conjugate base is left with a negative charge. Whenever we're ranking by acidity, we want to rank by the stability of our conjugate base. So the stability of our negative charge that our conjugate base has. In order to do this, we can use an acronym called AREO. A stands for the atom that loses a hydrogen and gains a negative charge. When looking on the periodic table, atoms going down and to the right of the periodic table are more acidic. So for example, comparing an amine versus an alcohol. The first thing that I like to do when ranking it by acidity is drawing what the conjugate base of our molecule looks like, meaning our acid after it's lost to hydrogen and gained a negative charge. So I'm going to go ahead and draw the conjugate bases of all these molecules, and then we can answer the questions. So I've drawn the conjugate bases of all my molecules, and now I can compare the stability of my conjugate bases. So going to the right on the periodic table, nitrogen versus oxygen. Oxygen is more to the right, meaning it's more electronegative. So more electronegative atoms can hold on to negative charge better. So an alcohol is a better acid than an amine. Going down on the periodic table, for example, sulfur versus oxygen. Sulfur is further down on the periodic table, meaning it's larger. Since it's larger, electrons can spread further out, and more spread out charges, less concentrated charges, are more stable. So sulfur is a better acid than oxygen. So now let's consider our letter R. R stands for resonance. When electrons can resonate, this is a delocalization of charge because electrons are moving around and delocalizing that charge, making it less concentrated and therefore more stable. So if we were to compare these two molecules, this molecule cannot resonate because the negative charge is not next to any pi electrons that could resonate. On the other hand, this molecule right here can resonate. And I'll show you what that resonance looks like. Both of these hydrogens were taken from oxygen, so the same atom, but since this conjugate base could resonate, it's more stable, so this molecule is a better acid. So now let's look at letter I, which I stands for induction. This is not referring to our atom, which gains a negative charge after it loses a hydrogen. This is referring to other atoms on our molecule. So if we have electronegative substituents on our molecule, these actually stabilize our negative charge because electronegative atoms like electrons, so they pull away electrons from our negative charge, making it less concentrated and more stable. So if we compare an oxygen with fluorine attached and an oxygen with nothing attached, our oxygen with fluorine attached is a better acid because fluorine stabilizes our conjugate base by pulling away electrons from this negative charge. On the other hand, if we have electron donating substituents, so here we have a carbon group, which isn't very electronegative, so I'm going to call it electron donating. This actually pushes electrons towards our negative charge, making it more concentrated and less stable. So comparing these two molecules, this molecule has electron donating carbons attached versus this one does not have as many carbons. So this one is more acidic. So now let's look at our last letter, which is O, orbital. sp hybridized hydrogens are most acidic, then sp2, and sp3 hybridized hydrogens are the least acidic. This is because sp hybridized orbitals are smallest, meaning the electrons are attracted to the positively charged nucleus. The positive charge of the nucleus will be balanced out by the negative charge of the electrons, therefore making that negative charge less negative and more stable. So if we compare these two molecules, this molecule has an sp hybridized negative charge. That negative charge is balanced out by the positive charge of the nucleus since this orbital is smaller. So because of that, this molecule is more stable, so this is a better acid. So let's look at an example question of ranking by acidity. The first step to any ranking by acidity question is drawing the conjugate base. So drawing our acid after the acidic hydrogen has left and the atom that had that hydrogen gains a negative charge. So I'm going to go ahead and highlight all of the hydrogens that I will be removing or deprotonating and draw what our conjugate base looks like. So now that I've drawn out what all of our conjugate bases look like, the first thing I want to do is look to see if our conjugate base can resonate. Because if it can resonate, this is a delocalization of charge, making our charge more stable. Automatically, I'm noticing that these two have negative charges that are next to pi bonds, therefore they can resonate. And I'll show you what that resonance looks like. So these are the two molecules after they've resonated. Now I want to look to see the atoms that are carrying the negative charge in the resonance structures of each molecule. So I can see here the negative charge is on an oxygen and another oxygen. Here though, our negative charge is on a nitrogen and an oxygen. Nitrogen does not carry negative charge as well because it's not as electronegative. So I'm going to say that our molecule that has a negative charge resonating across two oxygens is our number 1. And our molecule that has a negative charge resonating across nitrogen and oxygen is number 2. So since none of our other molecules can resonate, we want to look at the atom that's carrying the negative charge in our other molecules. Here we have a negative charge that's on sulfur, and in these two molecules, in both of them, the negative charge is on nitrogen. When we look at the Bean rule and the periodic table, atoms going down and to the right on the periodic table are more acidic. So sulfur will carry negative charge better than nitrogen because it's larger, so it's able to spread out that negative charge better and make it more stable. So sulfur is going to be a better acid, so I'm going to rank it number 3. When deciding between which one will be ranked 4 and which one will be ranked 5, I want to now look at inductive effects. Since both of these negative charges are on nitrogen, the only thing that's different is other atoms on the molecule, so other inductive effects. With inductive effects, we need to remember that more electronegative atoms will withdraw away electrons from this negative charge, making it more spread out and more stable. When comparing fluorine and chlorine, looking on the periodic table, this E right here represents electronegativity. Fluorine is more electronegative than chlorine, so it'll pull away more electrons from this negative charge, making it more spread out and more stable. So because of that, this is a better conjugate base, so this will be our better acid. So I'm going to rank this number 4, and I'm going to rank this number 5. So I've written out a guide for you guys explaining the steps as to how to approach ranking by acidity questions. Feel free to screenshot it, take notes, whatever you need to do to help this make sense.